Hi guys, how are you doing? Welcome back to Physical Chemistry Lecture Series. Today we are going to discuss about classification of chemical reactions. Classification of chemical reactions. Classification of chemical reactions. So today we are going to discuss about the classification of chemical reactions. We have the several important reactions. For our convenience, we are classifying them into different types on the basis of different factors. So in order to classify the chemical reactions, we should take the three important factors. So the first one is nature of reaction. Second one is rate of reaction, and third one is mechanism of the reaction. So we are taking the three important factors. First one is nature of the reaction, second one is rate of reaction, and third one is mechanism of reaction. If you take the first one, so first factor is nature of reaction. Nature of reaction. So on the basis of nature of reaction, we have the five important chemical reactions. Okay. So on the basis of nature of reaction, chemical reactions are divided into five types. So they are divided into five types. One is combustion reaction. One is combustion reaction. Second one is combination reaction. Second one is combination reaction. Third one is decomposition reaction. Decomposition reaction. Fourth one is displacement reaction. Fourth one is displacement reaction. And fifth one is redox reaction. Redox reaction. On the basis of nature of the reaction, chemical reactions are divided into five types. So one is combustion reaction, second one is combination reaction, third one is decomposition reaction, fourth one is displacement reaction, and fifth one is redox reaction. So now let us take the combustion reaction. So if a chemical compound is combined with the oxygen, then it is called as the combustion. For example, let us take the alkenes or alkynes are simply hydrocarbons and combined with the oxygen. Then we can get the carbon dioxide and water. So it is the best example for the combustion reaction. So combustion reaction means the chemical reactions in which a material is combining with the oxygen. Then it is called as combustion reaction. So it is simply CXHY. It is combining with the oxygen. Then we can get the X moles of the carbon dioxide plus Y moles of the water. Plus we can get the energy. We can get the energy. It is negative only. So this is our best example for the combustion reaction. And second one is combination reaction. So combination reaction means the chemical reactions in which two molecules are combined together. So that reactions are called combination. For example, let us take the reactant A and combine it with the reactant B. Then we can get the product AB. So here two molecules are combining and giving the an exchange product. That's what is called as the combustion reaction. And the third one is decomposition reaction. So decomposition reaction means a substance will be undergoes decomposition. So that type of the reactions are called decomposition reactions. Take the AB. So AB on thermal decomposition, we can get the A plus B. So that is about the decomposition reaction. And fourth one is displacement reaction. So this displacement reaction is again can be divided into the single displacement reaction. Single displacement single displacement reaction and double displacement reaction. Double displacement. So these are nothing but the substitution reactions. The chemical reactions in which one substituent is replaced by the another substituent is called as displacement reactions or substitution reactions. For example, let us take the AB. So if AB is combining with the C, so there we can get the AC plus B. So here B is coming out from the A reactant and C is combining. So that means C is displacing the B. So that's why it is called as the substitution reaction or displacement reaction, and here it is displacing the one substituent, hence it is the single displacement reaction. Whereas in the double displacement, two substituents will be displaced. For example, let us take the AB. If we combine with the CD, then we will get the AC plus BD. So here two molecules undergoing the substitution. That's why it is the double displacement reaction. And last one is redox reaction. Redox reaction means the chemical reactions in which reduction and oxidation both will be takes place. So they will be called as the redox reaction. For example, take the electrochemical reactions. Best example is zinc. If zinc solid is combining with the copper sulfate, so then we can get the zinc sulfate plus copper solid. So this is the example for the redox reaction. So because you take the zinc, so zinc in the reactant cases it is in the 0 oxidation state, whereas in the product cases it is in the +2 oxidation state. So here it is 0, here it is +2. So it is converting into +2 state. Whereas if you take the copper, here it is in the +2 state and converting into the 0 oxidation state. So one is undergoing the oxidation and another one is undergoing the reduction. So that's why it is the redox reaction. So this is about the classification of chemical reaction on the basis of nature of reactions. And the second factor is rate of reactions. Second factor is rate of reaction. So rate of reaction. On the basis of rate of reaction, so again chemical reactions can be divided into three types. So first one is the nature of reaction, second one is rate of reaction. So on the basis of rate of reaction, we have the three types of chemical reactions. So one is extremely slow reactions. Second one is moderate reactions, and third one is fast reactions. Fast reactions are instantaneous reactions. Okay, extremely slow reaction, moderate reactions, and fast reactions. So first one is extremely slow reactions. Extremely slow reactions. Extremely slow reactions means the chemical reactions which proceed with very low rate are called as extremely slow reactions. Okay, the chemical reactions which proceed with very low rate, so they are called as extremely slow reactions. For example, let us take the conversion of diamond into the graphite. So take the diamond. So diamond is converting into the graphite. So for this reaction, delta G naught is equal to minus 2.9 kilojoules per mole. Whereas if you take the rate, so rate is equal to very low. So that's why it is extremely slow reaction. Second one is take the hydrogen and combining with the water. So there you can get the take the hydrogen and combine with the oxygen, then you can get the water. So it is the gas. So this is also gas and it is the liquid. For this reaction, delta G naught is equal to negative, whereas rate is equal to very low. Very low. Hence this belongs to the extremely slow reaction. And third one is you take the hydrogen and combine with the nitrogen. So on combination we can get the NH3. We can get the ammonia. So hydrogen is a gas, hydrogen also gas, and ammonia is also in the gas phase. So for this reaction, delta G naught is equal to 0, whereas R is equal to very low. So these are the best examples for the extremely slow reaction. So all the cases rate is low. So they are example for the extremely slow reactions. And second one is moderate reactions. Second one is moderate reactions. So let us take the moderate reactions. Moderate reactions. Moderate reactions. Moderate reaction means the chemical reactions which proceed with measurable rates are called as moderate reactions. Okay, so the chemical reactions which proceed with measurable rates are called as moderate reactions. So let us take the example. So if we take the example, first one is, let us take the sodium metal. Sodium is the solid, combined with the chlorine gas, then we can get the sodium chloride with the solid. For this reaction, delta G naught is equal to negative. So whereas R is equal to, so it is moderate. So its rate is measurable, hence it is moderate reaction. So otherwise, take the decomposition of the hydrogen peroxide. So it is H2O2. It is a liquid. So on thermal decomposition, we can get the H2O plus oxygen. So here it is the liquid and this is the gas. For this reaction, so let us take this stoichiometry 2 moles and 2 moles, then we can get the 1 mole of the oxygen. So if you take the standard Gibbs free energy change, it is negative, and if you take the rate, it is measurable, so it is moderate. So this reaction also proceeding with the measurable rate, hence it is also moderate reaction. Otherwise take the decomposition of carbonic acid. So it is H2CO3. It is the liquid or aqueous. Take the aqueous phase. So on thermal decomposition, we can get the H2O liquid plus carbon dioxide gas. So here also delta G naught is equal to negative, whereas rate is moderate. So these are the best example for the moderate reactions. Otherwise, all the organic reactions are proceeding with the measurable rates. So that is for the fourth example. And the last one is fast reactions or instantaneous reactions. Fast reactions are instantaneous reactions. Fast reactions are instantaneous reactions. Okay, so it is fast or instantaneous reactions. Instantaneous reactions. That means the chemical reactions which proceed with very high rate are called as fast reactions or instantaneous reactions. So their rate is very high. So we are unable to measure their rate either by the conventional methods or conventional methods. So that's why it is the fast reactions. So best examples. Let us take the examples. So best examples are ionic reactions. So one is ionic reactions. Ionic reactions. For example, let us take the silver nitrate AgNO3 combined with the sodium chloride. So if you combine, so here what happens, we can get the silver chloride as the solid plus you can get the sodium nitrate. It is in the aqueous. So it is also aqueous. It is also in the aqueous phase. So it can be proceeds with high rate. Hence it is the fast reaction. So otherwise neutralization reactions. Neutralization reactions. So that means acid-base reactions. For example, take the HCl. Take the HCl and combining with the sodium hydroxide NaOH. So it is aqueous. It is also aqueous. So on combination you can get the sodium chloride NaCl aqueous plus you can get the water. So this is about the examples of fast reactions or instantaneous reactions. So next one is classification based on the mechanism of reactions. Classification based on the mechanism of reactions. Classification based on mechanism of reactions. So third factor is mechanism. Okay. So on the basis of the mechanism of the reactions, all the chemical reactions are divided into two types. One is simple reaction and second one is complex reaction. So let us take this in the their different tube form. So that's why first one is simple reactions. So we are taking the differences. So here first one is simple reaction. First one is a simple reaction and second one is complex reaction. Complex reaction. So on the basis of the mechanism of the reactions, chemical reactions are divided into two types. One is simple and second one is complex. So if you take the simple reactions, the chemical reactions which proceeds through single step are called as simple reactions or single step reactions or elementary reactions. Okay, so the chemical reactions which proceeds through single step are called as simple reactions or single step reactions or elementary reactions, whereas the chemical reactions which proceeds with several steps or sequence of single steps are called as complex reactions. Okay, so the chemical reactions which proceeds with several steps or sequence of single steps or sequence of elementary steps are called as complex reactions. So that's why first difference is, so these are proceeds through single step. Simple reactions are proceeds through single step, whereas complex reactions are proceeds through several steps. Okay, so proceeds through several steps or sequence of elementary steps. These are proceeds through sequence of elementary steps. Second difference is Simple reactions are proceeds through formation of activated complex or formation of the transition state. So here we have the transition state. Whereas if you take the complex reactions, they also they also proceeds through the formation of activated complex or proceeds through the formation of the transition state. So both the cases we have the transition state. So if we want to see this transition state, we have to take the energy profile diagrams of simple reactions as well as the complex reactions. So now we have to take the energy profile diagram. So if you want to take the energy profile diagram, just we have to take the two parameters. One is potential energy and second one is reaction coordinate. So we have to plot the graph between the potential energy and reaction coordinate. So this is the x-axis and it is the y-axis. So on the y-axis we have to take the potential energy, whereas on the x-axis we have to take the reaction coordinate. Reaction coordinate or reaction progress. So both the cases we are taking the energy profile diagrams. Energy profile diagrams. So it is the origin. Here also we have the origin. So on the x-axis, we are taking the reaction coordinate. Reaction coordinate. We are taking the reaction coordinate, whereas on the y-axis, we are taking the potential energy. So now let us come to the simple reaction. So in the simple reaction cases, so if you plot the graph between the potential energy and reaction coordinate, so we can get the figure in this way. So this is about the reactant and it is about the product, and this is the transition state. Okay, so this is the transition state or formation of the active complex. Okay, so this energy corresponds to the reactant energy, whereas this is corresponds to the product energy. And the energy corresponds to the transition state is the threshold energy. So the energy difference between the threshold energy and reactant energy is called as activation energy of forward reaction. It is the activation energy of forward reaction, whereas the energy difference between the product and activated complex is called as the activation energy of backward reaction. Activation energy of backward reaction, and the energy difference between the reactant and product is called as enthalpy. Okay, is called as enthalpy. So if we want to calculate the enthalpy, it is equal to activation energy of forward reaction minus activation energy of backward reaction, and this activation energy is generally is equal to threshold energy minus reactant energy. So this is about the energy profile diagram, which is indicating the formation of the transition state. Okay. So if you take the energy profile diagram for the complex reactions, so there also we have the reactant. So there also we have the reactant and product. Yeah. So this is the reactant and it is the product, and this is the transition state 1, whereas this is transition state 2, and this is transition state 3. Transition state 3. And this is the activation energy EA1. whereas this is EA2, whereas this is EA3. Okay, so if you see the energy profile diagram for the complex reaction, so there we have the two reaction intermediates, whereas in the simple reaction we don't have the any intermediate. So therefore, therefore simple reactions doesn't have any reaction intermediate. Okay, so in simple reactions we don't have any reaction intermediate. Okay, that is the third point. So no reaction intermediate. Whereas in complex reactions they can be proceeds through formation of reaction intermediates. So proceeds through reaction intermediate. Proceeds through formation of reaction intermediate. So it is about the difference. And fourth one is so here if you want to calculate the rate, so rate is equal to minus dr by dt. It was given by the simple reaction, whereas in the complex cases the overall rate is given by the slowest step of the reaction. Okay, so R overall is equal to dr by dt. So it was generally given by the slowest step of the reaction. So slowest step means that step should have the highest activation energy. So if you see these activation energies, here one is the higher one, then it will be act at the slowest step of the complex reaction. Then it will give you the overall rate of the reaction. That is about the fourth point. And fifth one is if you take the molecularity, so molecularity can be defined by the simple reactions. Okay, so molecularity can be defined. Molecularity can be defined. Whereas for the complex reactions, molecularity is not defined. Okay, for complex reactions, molecularity is not defined. Further, so molecularity of the elemental step should be given. Okay, so the overall molecularity is not given. Whereas for each step, we can able to define the molecularity. So that is about the fifth point. And next one is, so if you will take the simple reactions, in simple reactions, products are directly formed from the reactants. Okay, so here products are directly formed from the reactants. In simple reactions, products directly formed from reactants. Whereas in complex reactions, the products are not directly formed from the reactants. Okay. So in this case, they are not directly formed from the reactants. So products are not directly formed from reactants. Not directly formed from the reactants. And next point is, if you take the order of simple reaction, so order of simple reaction is very small. Okay, order of simple reaction is small and it is always less than or equal to 3. So order is small. Order is small and less than or equal to 3. Whereas if you take the overall order of the complex reaction, it is larger and always greater than 3. Okay, so order order is large, larger and greater than greater greater than 3. Order is larger and greater than 3. And the next point is, so next one is rate constants. Next point is rate constant. So if you take the experimental rate constant values, so for the simple reaction, the experimental rate constant values are similar with the calculated rate constant values. Okay, so in the simple reaction, the experimental rate constant values are equal to the calculated rate constant values. Okay, so K experimental, so almost equal to K calculated. Yeah, calculated. K calculated. Whereas in complex reactions, the experimental rate constant values differ with the calculated rate constant values. For the complex reactions, the experimental rate constant values differ with the calculated rate constant values. So these are important differences between the simple and complex reactions. So now I have to stop here. Tomorrow we will continue.